Good morning, everybody. My name is Sam Dhaliwal. I'm going to be mediating this presentation. Welcome to this webinar hosted by IPCOS on optimal base layer controls for distillation columns. We are pleased to share some of our experiences and knowledge with some of our customers and potential customers and the wider audience out there. The presentation will be done by Juan Carlos. Juan is an experienced APC engineer who's been working with IPCOS. He has more than 6 years of experience in process control and has successfully deployed several APC projects in Europe, Middle East, and Latin America. Juan is based in Cambridge, in the IPCOS office in Cambridge, and I shall now pass it on to Juan to continue.
Thank you, Sam. Good morning, everybody. Again, we're going to be talking about optimal base layer controls for distillation columns. The following is the agenda to follow on this webinar. First of all, we're going to talk about the pressure control for a heat pump driven C3 splitter column. Then we're going to talk about a methanol water column on which the impurities are a difficult thing to handle. To finalize with cut point temperature control on an extractive distillation column. To finalize the slides, we're going to give some general guidelines on what is important to keep into account at all times when designing or redesigning base layer control strategies. Okay. Pressure control for a heat pump driven C3 splitter. Challenges we typically face on C3 splitters: narrow boiling point difference, high pressure operation, that's typical things, high vapor to liquid traffic, high purity products, typically high energy requirements, hence the need for heat pumps, and very flat temperature profile and low relative volatility. This is not an easy separation to do. Typically very large columns, more than 100 trays in general. And here are some common control strategies for those columns. As for the pressure can be floating at times when there are real constraints on the condensing part of the column. But as well, you can see pressure being controlled by typical hot bypass control or by flooded condenser control. Then the top level, depending on how big the reflux ratio is, which at the same time is depending on how pure you need to get your propylene, you use either reflux or distillation to control the top level. For the top impurities, then depending on what you decide on your top level, you can use the distillate as means of controlling your impurities on the top. You can use the reflux ratio, or even you can use things like feed to distillate ratio, distillate to feed ratio, or make the calculation and control the real internal reflux to the column. On the bottom, the impurities can be controlled with the boil-up ratio, or even with the bottom flow if you, for example, have, as we're just saying in the next topic, the bottom level being controlled by the boil-up. If the bottom level is being controlled by the boil-up, you can actually control the bottom impurities with the bottom flow. But you can also have the option of, if you have enough flow, to control the bottom's level just with the bottom product flow. For those not completely aware of what a heat pump is, well, a heat pump is a device that helps you to raise low-grade heat to a temperature at which the heat can be utilized. The heat pumps, basically, what they do, as we see here on the graphic, is they take the overhead vapors, and through the compressor, they raise both pressure and temperature of those vapors, allowing them to be a good heat transfer medium to send heat to the reboiler. So it's basically using all this latent heat, but now at a higher temperature, enable it to heat the reboiler of the very column. This is what is shown here. If you see, the overhead vapors are compressed and sent partly to the reboiler. This reboiler and this reboiler are the same, just a matter of the graph to make it a bit more clear. It's the same heat exchanger, and then you use the vapors compressed to give duty to the column. In the specific case that we're gonna talk about, this plant had no control of the top pressure, and that was giving them real troubles in trying to keep the top impurities in control. As well, it was giving them issues trying to control the duty to the column. After giving it a thorough analysis, well, we noticed the following. First, let's talk a little bit about how a centrifugal compressor with inlet guided vanes works. That was the case in that plant. It was just inlet guided vanes acting on a motor centrifugal compressor. These are the performance curves that you typically see on those compressors. The performance curve change with the opening of the inlet guided vane, as you can see here. The more open or the less restrictive the inlet guided vane is, the higher the flow and pressure you can achieve with the compressor. So the reason why they didn't have this pressure under control was because the initial approach, the initial design they had for it, was to try to control or regulate that pressure with the inlet guided vanes. Regulate the pressure moving the inlet guided vanes. It was never working, and the reason why is explained here. If you just make a simple material balance around this envelope, the pressure is not different than just the effect of the material balance around this point. So that's why we're making this material balance on the time domain, let's say. So what's going in is the vapors coming from the column, and what's also coming in is the reflux going back to the column. And what's going out from this envelope is a compressed flow. Fair enough till now, but the thing is, if you look at it in more detail, you notice that because, as we just said here, the level is being controlled by the reflux. If you open the inlet guided vanes, at the end what you do is you compress more flow. That flow becomes into more condensate here and sends more flow back to the column. That increases the reflux, which means that both the reflux and the compressed flow are a function of the percent opening or the angle of the inlet guided vanes. This is by all means something that will never work because it's not having the effect it is intended to have. It was originally designed like this, probably expecting that by restricting less the flow inside the compressor, you will somehow deplete from vapors this section and the pressure then will decrease. But the fact of the matter is that's not happening because most of the flow is actually coming back to the column. So if anything, when you make moves in the inlet guided vanes, the pressure can increase. That's why we say here the dynamics are slow, and you see an inverse response, because at first what you have is, yes, when you change the inlet guided vanes, the pressure dynamically or quickly decreases, but just after a couple of minutes it starts increasing back again, because the increased flow becomes into more condensated, more reflux. So it's basically a vicious circle. You will never get out of it. That was not only the problem, the problem was also that while doing it, moving the IGVs, you're not exactly moving in a line like this. You're moving more like towards these extreme points of the performance curves. If you draw a line here, which is sadly not drawn, this is nothing different than the source line of the compressor at each in each one of the cases, at each opening of the inlet guided vanes. So when you do that, what you're actually doing is approaching the source condition. That is also suggesting that if you try to control your pressure with your inlet guided vanes, you can probably face issues with your compressor performance. So what we did was just look at the whole picture, and not only the little part in which only the compressor and the vapors are considered, and we extended the envelope to also consider the condensate part. Let's go back a bit to the drawing. If you see here, the vapors are split into two. One part, the biggest part is going through the reboiler, but there's a small part that you can actually regulate how much you want it to go through this way, and it's a part that is going through a cooling water condenser, an auxiliary condenser. And if you look at that using the same approach, well, then you can see that if you write down the material balance, the reflux will still be a function of the inlet guided vanes position, but in this case the condensate, which is nothing different than the reflux, the condensate will be a function of the inlet guided vanes, the pressure, but will also be a function on how much you let the vapors go through the auxiliary condenser. That decouples the whole system and allows you to make proper regulation, because if you do changes in this valve, that at the end will not have the same effect as changing the inlet guided vanes. Not only that, you will be working all the time probably at the same point in the performance curve of the compressor, avoiding coming close to source and keeping the efficiency of the equipment more constant. So the new strategy, as we just said, was basically to control the top pressure with this bypass valve that regulates the flow through the auxiliary condenser, cooling water condenser. And here's the result. Before, they were pretty much unable to control it. They were trying to manually make changes on this bypass, and also trying to make changes on the inlet guided vanes to keep the pressure as controlled as possible. This is what you see here is basically them trying to put the old configuration in automatic, in which the pressure was controlled by the inlet guided vanes. You see how the response is very big and the regulation is very poor. And after we did the study and implemented the new strategy, well, it just shows as very smooth control, very tight control. Of course, it's not only the design of the new strategy, it's also the tuning of it, and that we did using our PID tuning software, Aptitune, and it allowed us to make proper tuning for this loop. This loop, as maybe all of you know, behaves just like an integrator. That's something you can specify in our software, and it will give you the proper PI parameters for you to tune it and have it control in a very stable and robust way. Okay, so let's continue on. Second example, methanol water impurities control. What are challenges you typically face in a methanol water system? Well, you typically need an ultra-high purity product. We're talking about 99.9999% methanol on the top. That is directly related to having high energy requirements. It's a very flat temperature profile on the top 50 trays of the column. And the final challenge that you have is that you have impurities that are a mid-cut. The impurities in this system are typically heavier alcohols like ethanol or propanol. Those alcohols are, of course, heavier than methanol, but lighter than water. So that's why they become mid-cut impurities, and you need to get rid of them before they build up in your system. So this is an schematic of the column. As you see, we have the feed coming inside. We have our methanol and the water, but also the impurities. And you see how we have this little bump in this part of the column where the impurities need to be drawn. So, what was the configuration before IPCOS starting to work on this? Well, pressure control with the fin fan coolers, level control with the reflux, a reflux ratio controller acting on the top product, a draw flow controlled by a temperature in a downstream column, temperature of the draw tray controlled by the feed to the column, and finally the reboiler flow controlled just by condensate outlet. Problems. Well, first of all, throughput instabilities, poor impurities removal, big duty variations, very poor pressure regulation, and poorly tuned top level. All of them at the end interrelated problems. So in this case, what we did was we took the whole column. Our approach was the whole column, not loop by loop. And then we noticed we had to do stuff in several parts of the column to improve the behavior. So first of all, what we did was we retuned this level controller that stabilizes the flow back to the column and also stabilizes this reflux ratio controller. After that, we use this pitch control on the pressure, in which what it's done is using of the filter PV as set point of the pressure. This at the end, what does is it keeps the pressure floating but not changing drastically like it used to do before. Before, because the set was constant, the fin fan coolers were pretty much just open. The fins were opening and closing all the time, and no real regulation was done. Here, the pressure was, let's say, changing with the atmospheric conditions, but in a much more smooth way, which reduced disturbances to the rest of the operation. As well, the draw flow was not anymore controlled by a downstream operation. The draw flow was controlled by a ratio controller, because we noticed that the percentage of impurities coming in the feed were almost the same all the time. So you can adjust this ratio controller if you need to, but we noticed that it was pretty much not needed in most of the cases. Just setting a proper ratio value was enough to keep this in control and to also stabilize the amount of impurities coming out of the column. On top of that, because the pressure was now going to be, let's say, floating, we implemented a pressure compensated temperature controller for the draw tray that grants you keeping your impurities composition constant all the time, regardless of the pressure changes in the column, using the same handle, which was the feed flow to the column. And if you remember, we were talking about big duty variations. Those duty variations were mainly due to pretty much uncontrollability of the level in the reboiler. This reboiler was just a steam reboiler. The level of that steam reboiler determines the heat surface, the heat transfer area. And if you have this level going up and down, well, then the duty is pretty much not controlled. You will just vary with it. So what we did here was we implemented feed-forward control to help this level controller to act on the condenser output by keeping an eye. This flow here is the steam flow coming to the reboiler, and we also were looking at the temperature, at the bottom temperature of the column. If it was too high, it was probably because too much heat was being put into the column, and then a correction was done on a feed-forward action. So the results of this were that we had a much tighter overhead drum level control just by doing proper tuning. The pressure compensated temperature control on the draw tray, which allowed better impurities separation. Feed-forward action control on the bottom level, as you just said, which stabilized the duty to the column. And the pitch control on the fin fans for the pressure regulation, which allowed us to have much smoother changes in the pressure. The results, the results are shown here. As a result of just better tuning the top level of the column, we see how the reflux came from changing all the time. You see this low frequency oscillation all the time on the reflux, which is the result of poor tuning on the top level. After that, we managed to keep the reflux much more stable because the level was much better tuned. Not only that, this is the final control element, the controller output. You see how it was all the time under a lot of stress, going up and down, very high frequency oscillation on it. And after that, much less variation. So two very important achievements here. Again, results of better tuning on the top level were better control of the reflux ratio on the top. You see how this reflux ratio was pretty much all over the place before. And after that, after tuning, it stabilized. It was much smoother. Same as with the final control element. The top level itself, well, this is just the proof that this was the issue. This was the cause of it all. Top level just going up and down all the time. After we did the tuning, it went much, much smoother. And that, of course, if you don't have a reflux changing all the time, then you don't have vapors going up and down the column all the time. This stabilizes your temperature profile in your column. And on top of that, remember we implemented a pressure compensated temperature for this column on the draw tray. This is the side cut temperature we were talking about. So before we were seeing changes plus or minus 4 degrees. This is a high purity column, and the impurities, well, are very sensitive to this temperature. After that, we managed to really reduce those variations on the side cut temperature, meaning that we were able to much better control the side cut composition and avoid buildup of impurities in the column. Okay. That's it. Thank you. And final example, the cut point temperature control on an extractive distillation column. In this case, it's an extractive distillation column using NMP as solvent to separate non-aromatics from benzene. The top distillate should not have more than 3% benzene, should be mostly non-aromatics. That's the whole purpose. And you don't want a lot of benzene to slip from it because this is a benzene plant. This is your main product. So if you lose benzene on the top, then you're losing product. On the bottoms, we have the solvent with the extracted benzene, which is afterwards separated on a stripper column. And the solvent, of course, is recycled back to the extractive distillation column. This is the process, so we just explained it. You have the non-aromatics on the top, the solvent and benzene going to the stripper, benzene being stripped from the solvent, and the solvent pumped back to the extractive distillation column to continue on the separation. So what we found once we were there was that this was the control strategy that it had in place there. The temperature controller was acting on a ratio controller. This ratio controller was keeping the ratio between the amount of benzene in the feed. This ratio is actually the amount of the percentage of benzene in the feed with the amount of solvent. That meaning that if more benzene was going to the column, then this ratio controller was sending more solvent to the column as well to keep the separation, let's say, at the same state. The problem was that although this temperature here, the tray 49 temperature, is actually a very good indication of the benzene slip in the top distillate, the ratio controller was actually not that good of a handle to keep that temperature under control. That led to very poor, bad, sluggish control, and a lot of interaction was seen with the reboiler steam. If you see here, we have the reboiler steam being changed by a bottom temperature controller. This already can tell you there's something going on there. You have two temperature controllers on the same column. You can see here the behavior. This is the solvent flow. The solvent flow can just change and change and change, and pretty much no effect on the temperature of the tray 49 is seen. So yeah, very sluggish, pretty much not control is in place. That needed to be fixed. Here you can see how that temperature on the tray actually correlates very good with the benzene slip. This is data taken from the plant. So basically what we noticed was that the temperature was much more sensitive to the changes in the duty to the column than what it was to the changes in this ratio. So the decision was to change the strategy from controlling the temperature with the ratio to controlling the temperature with the duty to the column. That also needed as to pretty much break this controller, this original controller, this bottom temperature controller. And we notice as well that the bottom temperature is not a good quality indicator. I mean, it's not showing anything useful, whereas the top temperature is much more useful in the operation. So in the new base layer control, the temperature sets the reboiler steam flow, keeps a good cut point control, is now a tight control of the benzene slip in the distillate, which is a very important thing in this column, because it minimizes the benzene giveaway. Remember, this is the main product for this column. Afterwards, then the ratio of solvent to benzene content in the feed was set by the operator. They have their own controls in place to make the changes, and keeping the non-aromatics in the benzene at the high limit. This is the result. You can now see how, if you make a set point change, the process actually responds and reaches the new set point, both down and up, and it keeps at set point all the time. So it's not like before, in which you saw the ratio just going up and down, and having no real effect on the temperature. Here you can see a clear effect on the temperature, and that allows you to have a much tighter control, tighter cut point control, easier for the operator to optimize, because now he can easily keep the benzene slip in the top at the minimum. Also, it allows the operator to change this solvent to feed ratio at a minimum. Remember, the more solvent you use, the more energy you need to separate it from the benzene in the downstream column. The final benefit achieved is that now the column is APC ready, because now a good base layer structure is in place. As I said, to finalize, we're just going to give general guidelines that we learned from all these experiences. First of all, I think it's probably most important, heat, material, and even hydraulic balance should always be reinforced with base layer strategies. That means you should not fight nature with the base layer. The heat, material, and hydraulic balances are something you just need to live with. You need to reinforce it with the base layer. That's the only way they can actually work, as we saw in the first example. So the material balance was not reinforced in the original proposal they had. Proper PID tuning can bring a process back to stability. We saw that in the second example. Just by properly tuning the top level of the column, changes in the operation were very, very visible. As well, composition control is advisable where possible. Again, our second example of methanol water system. Well, it was easy to implement a pressure compensated temperature because it's a simple mixture, and it was very useful because afterwards it was very easy to keep the impurities on control on the column. And finally, probably coming from the last example, the manipulated variable for the base layer strategy can be chosen based both on proximity and or sensitivity. I mean, let's just remind this a little bit. Based on proximity, it seems like this temperature is likely to be controlled with the ratio easily, but it's actually not. It is much more sensitive to the duty to the column, although it's farther, let's say process-wise, is farther in the process than what it is the ratio, is much more sensitive, and the result is that a much better control is achieved that way. So yeah, sensitivities also needs to be taken into account when designing or redesigning a new base layer control strategy. Thank you for your participation. That was all for today.
Thank you, Juan. Please feel free to submit some questions through the chat window, and we'll try and answer them. And if we can't, we'll certainly email you the answers if we can't get to your question. Some other little things. If you would like a copy of the presentation, you can email us at info@ipcos.com, and we'll send that over to you. We also have the next webinar coming up, which will be on tuning cascade loops, and this is using our Inca Aptitune software. We have enhanced our software to include some functionality so you can tune cascade loops now. So that should be a very interesting one coming up, and the date will be announced on our website. You can see that coming up fairly soon. Now, while we're just looking at some questions coming in, there's one question here which has come in, which is in your C3 example, where you were using the condensate, the cooling water exchanger to control the pressure. How did you set the IGV in that situation?
Well, the IGVs in that case can be fixed, because the IGVs will have an effect much more on the duty of the controller than what it actually has on the pressure. And we just saw that the IGVs were left at the same position by weeks. I mean, weeks and weeks passed by, and they didn't have to change the IGVs of the column. No major changes in the feed to the column, and the pressure controller was still working. So in that case, yeah, the IGVs can be fixed. So that's not a problem.
Okay, thank you. We have a question here. How did we use the two feed-forward signals in the second presentation, the second example? How did you use the two feed-forward signals in I guess the PID strategy?
Oh, okay, yes. Yeah. Well, you mean like DCS, the details? If you want the DCS details, let's say, well, we can email that to you. But well, it basically was just taking the gains of those, the effect they had on the level, and put it directly to the output of the level controller.
Okay, so there's a mechanism in the DCS that allows us to do that.
Exactly.
Okay. Yeah. If there's any further question regarding that, please email us and we can clarify that further. There's another question coming here. How do you deal with process non-linearities in general terms when you're dealing with?
Oh, well, the good thing about using our tuning software is that our tuning software always keeps an eye on robustness of the software. On robustness of the PID tuning. And by robustness, it checks what happens if the process gain changes by 2 times or 3 times, and how will the same tuning work in those different process conditions. So yeah, it's basically robust tuning, how we handle the non-linearities.
Okay, thank you. There's another question coming in here. You touched on it earlier. What is your view on having 2 temperature controllers in a column? Well,
in general, you can say that 2 temperature controllers in a column are not typically the best option. We just saw in the third example, it wasn't the best option, but it can change from case to case. One thing for sure is that you need to run a sensitivity analysis and see how collinear those 2 temperatures are. And if they're not completely collinear, then you probably need to check how feasible it is to find a tuning that allows you to keep both temperatures under control.
Okay. We have another question here. How long did it take to analyze and optimize the system on the methanol column?
Well, it's a very long study. We were at site for something near to a year, but in the specific case of that column was one of the most challenging ones. I think it was something like around 2 months to do the whole study for just that column.
Okay, so it was really quite a lot of exchange of information with the client to understand the historical operation and then obviously trying to find out the best possible operating scenario.
Yeah, it definitely was. Yeah.
Okay. Very good. Any other questions coming in? We will also put a recording of this presentation on our website. So those of you who would like to share the presentation with your colleagues, you can do so by using the link that we will provide on our website. So thank you very much for attending, and we look forward to seeing you in one of our future presentations. And thank you for your time.